Hi, welcome back. In this video, we're going to introduce L'Hopital's rule and show how to use it on indeterminate forms. So first, let's recall what an indeterminate form is. So remember when we had a limit like this. The limit as x approaches -2 of x squared plus x minus 2 over x plus 2. If we tried direct substitution, we would get -2 squared plus -2 minus 2 over -2 plus 2. And the numerator is 0 and the denominator is 0. We called that an indeterminate form of type 0 over 0. Notice I put 0 over 0 in quotes because it doesn't really mean a number, 0 over 0. It's just a symbol describing what's happening to that quotient. It just means the numerator is getting infinitesimally small at the same time that the denominator gets infinitesimally small. And we call it indeterminate because we don't know, we can't tell what's actually going to happen. We could have a number, it could be getting arbitrarily large, infinity or negative infinity, we just can't tell. So we call it indeterminate. And so remember how we dealt with this. We said that this limit of this quotient was actually equal to the numerator factors as x plus 2 over x minus 1. Notice we could cancel. And even though the functions aren't the same, the limits are the same. So the limit of our quotient is actually the same as the limit as x approaches -2 of the polynomial x minus 1. Even though the two functions are different because they have different domains, their limits are the same at -2. And remember what the graph of this looked like. So the graph of this quotient is a straight line with a hole. And when x equals -2, it's not defined. And that point that we've removed is -2, -3. And so when we do the limit, once we get the limit of a polynomial, we can use direct substitution. So we can plug in -2 there, we get -2 minus 1, which is -3. In the past, we had functions for which algebra always got rid of the problem. But there aren't always limits where we can use algebra. So for example, let's look at some other indeterminate forms. We're going to have actually two types. So there's the type 0 over 0, which we've just seen. And then there's another type called infinity over infinity. So a 0 over 0 type is a limit as x approaches a number of a quotient, or it could be a limit as x approaches positive or negative infinity of a quotient, where both the numerator and the denominator of that quotient are approaching 0 at the same time. So f of x is approaching 0 and g of x is approaching 0. So one example, another example of that is the limit as x approaches 1 of the natural log of x over x minus 1. Notice if you try to do a direct substitution, the natural log of 1 is 0. And also 1 minus 1 is 0. So we get a 0 over 0 indeterminate form. But also notice there's no algebra that's going to help us there. So infinity over infinity means you have a limit as x is approaching a number of some quotient, or x could be approaching infinity or negative infinity, but you have a quotient in which both the numerator and the denominator are approaching infinity at the same time, or one of them could be approaching negative infinity. So the point is you have a quotient and both the numerator and the denominator are getting arbitrarily large at the same time. That's called infinity over infinity. We don't know what's actually going to happen. So here's an example. Say you have the limit as x approaches infinity of the natural log of x over x squared. Notice that as x approaches infinity, the natural log of x is also approaching infinity. And also x squared is approaching infinity. So that has indeterminate form infinity over infinity. And there's no algebra that can help us. L'Hopital's rule says if you have one of these limits, the limit as x approaches a of f of x over g of x, or you could have a limit as x approaches infinity of f of x over g of x. And it has indeterminate form 0 over 0 or infinity over infinity. And as long as your two functions are differentiable, so f and g are differentiable functions, then the limit as x approaches a of f of x over g of x is actually the same as the limit as x approaches a of f prime of x over g prime of x. Or if your limit is as x approaches infinity, that limit is the same as the limit as x approaches infinity of f prime of x over g prime of x. And this always works as long as you get a limit, an actual number, or if the limit actually turns out to be infinity or negative infinity, it also works. So let's look at these two examples above. So the first example we're going to do is the limit as x approaches 1 of natural log of x over x minus 1. First, we note we have a 0 over 0 indeterminate form. So that tells us right away we can use L'Hopital's rule. So I always like to say this limit is equal to, and then I put a little LH subscript to tell my reader I'm now using L'Hopital's rule. I'm applying that rule. So that rule says it's the same as the limit as x approaches 1 of the derivative of the natural log of x over the derivative of x minus 1. And we're differentiating with respect to x. And so this is equal to the limit as x approaches 1 of 1 over x over 1. And now we can plug in 1 and we just get 1. So the limit turned out to be 1, even though we had an indeterminate form. All right, let's look at the second one. So we're looking at the limit as x approaches infinity of natural log of x over x squared. First, we note what indeterminate type we have. We have an infinity over infinity type. So we're going to use L'Hopital's rule, and this limit is equal to the limit as x approaches infinity of the derivative of natural log of x over the derivative of x squared. And so differentiating the top, we get 1 over x on top. In the bottom, we get 2x. And if we simplify, we get the limit as x approaches infinity of 1 over 2x squared. And we know that from the rational function theorem that this limit is actually 0. We had an indeterminate form where the top and the bottom were both getting arbitrarily large, but we found that the limit was 0 using L'Hopital's rule. Remember, you always differentiate the top and the bottom separately. You're not using the quotient rule for differentiation. It's a completely different rule. So we can also do this on one-sided limits. So let's take a look at an example of a one-sided limit where L'Hopital's rule helps. So let's look at the limit as x approaches pi over 2 from the right of cosine of x over 1 minus sine of x. Notice if we plug in pi over 2 in the top, cosine of pi over 2 is 0. And in the bottom, sine of pi over 2 is 1. So we get 0 over 1 minus 1. So we do have 0 over 0. So we're going to apply L'Hopital's rule. And L'Hopital's rule says this limit is the same as the limit as x approaches pi over 2 from the right of the derivative of the cosine of x over the derivative of 1 minus sine of x. And so after we differentiate, we get the limit x approaches pi over 2 from the right of negative sine of x over negative cosine of x. And that's the same as the limit as x approaches pi over 2 from the right of the tangent of x. So can we plug in pi over 2? And the answer is no. This is undefined. This does not exist. Let's take a look at the graph of the tangent of x to figure out what this limit has to be. So remember, the graph has a bunch of vertical asymptotes. There's the vertical asymptote at x equals negative pi over 2. There's one at x equals positive pi over 2. And the third one that I drew was at x equals 3 pi over 2. Those are vertical asymptotes. And so remember, tangent has period pi, and it has infinitely many of these vertical asymptotes. And remember that tangent is always an increasing function, and the graph looks like this. So it goes through the origin, it goes through pi, and then it just keeps repeating. It'll go through 2 pi, it'll go through negative pi, negative 2 pi. It keeps going on forever. But we're only really interested in one part of it. So now we're interested in the limit as x approaches pi over 2 from the right. So we're looking at as x approaches pi over 2, that middle vertical asymptote, but we're coming from the right. And notice what the y coordinates are doing. The y values are going down, and they're going down to negative infinity. So the limit as x approaches pi over 2 from the right of the tangent of x is negative infinity. All right, remember that L'Hopital's rule really only works on indeterminate forms of type 0 over 0 or type infinity over infinity. But there are 5 more indeterminate forms, but you have to transform them into one of these 2 types of quotients. And in the next few videos, we'll see examples of how to do that. All right, I'll see you all there.